Talk is by Aicke Hinrichs. Aicke, you are welcome.
Thank you, Volodya, and many thanks to the organizers for inviting me here to this nice place in Cambridge. I'm already here for about 2 weeks and the weather was great. Thank you for that too. And thanks for the opportunity to give this talk here. I'm going to talk about random sections of ellipsoids, which sounds kind of geometric. But for this audience, I somehow prefer the second part of the talk, power of random information, because that somehow continues or fits into the subject of information-based complexity, which was introduced by Henrik. So I basically just recall some notions I use here. And we already had last week 2 introductory talks by Erich about that, but of course not everybody was there. So what is this random information I want to talk about? I will do that in the introduction after a short recall what Henrik already basically told you. I will talk about what we want to study here, what do we mean by power of random information. Then I will present a nice, easy, clean example which is basic and which can tell you somehow what you can expect. So this example is just approximation of Lipschitz functions, univariate Lipschitz functions, and what is the difference between optimal information, optimal algorithms, and random information. And then I will come to the topic of my talk, which is L2 approximations or approximation of functions from a Hilbert space, but with random information. And this is what we did in this joint work. I should mention my co-authors, David Krieg and Erich Nowak from Jena, Joscha Prochnow from Graz, and Mario Ulrich from Linz. Okay, so I talk about the problem which we studied in this paper, and then I go on to present some results, some ideas of proofs, and so on. Okay, let's start with the introduction. I want to stay in this context of information-based complexity as sketched by Henrik. So we have a numerical problem we want to study. In our case, this is a linear problem, a linear solution operator. Let's call that S. But Henrik used here indices N and D indicating the dimension or the number of variables. This is not important in my talk, but in the background you can think also about some spaces of higher dimension here. So F is a space of inputs, and we assume that F is a normed space here. Later on we will also assume that it's a Hilbert space. And basically you take functions from F, and your a priori knowledge is that it is in this space. So the norm of F somehow tells you about your a priori knowledge about the functions you want to approximate or integrate or whatever. And then you have the solution operator mapping to G. This can be the identity for approximation. It can be the integral for integration. And then G would be R for the integral, or it would be a function space where F is embedded for approximation. So the norm on G shall also be a normed space. The norm on G will be used to measure the error. Okay? So think of LP, L infinity, or L2 approximation, then G is such a Lebesgue space. Okay? Examples are, as I said, integration and approximation, and what information can we gather about the function F from our input set. This is linear information. We can ask n linear questions to our function. We have n linear functionals, L1, L2, and so on, up to Ln. And altogether this gives me this information operator which I can access about the function F, and it puts out a sequence of numbers, n numbers. And sometimes these are just function values, f of x1 up to f of xn. Sometimes those are linear functionals like Fourier information and so on. That's why I wrote here this information can be restricted to a subclass like n function evaluations. And what do you do with your information? You want to approximate the solution S of f, right? So what you do is you take your n numbers and combine them in a certain way. This can be a non-linear algorithm here, whatever. Any mapping from Rn to G gives you the algorithm by combining the information mapping with this reconstruction mapping phi. So we have information and reconstruction. Phi is arbitrary. The information mapping should be thought of as linear. Okay. And then we want to know how we are doing with this thing. And this was also introduced by Hinrichs. We have the worst case error of the algorithm an, which was phi after nn. So we measure the real solution SF, and we measure the difference with what the algorithm gives us in the error norm of G. Okay, so this is the error for the function f, and we take the worst case error. Our a priori knowledge is that f is in the unit ball of the space f. So our inputs basically are in the unit ball of f. Okay, and the main emphasis in my talk will be, okay, we somehow have fixed the information map, but we want to use the optimal phi. Okay, the phi should be optimal. And if you look at this formula, then if you take the minimal, what you can get for the error, the inf over all phi, this is basically the so-called radius of information. And I don't put a formula here showing you that it is a kind of radius. That comes in the next two lines. Let's look at a real radius. This is the radius of information at 0. And it is just the maximum of the norms of SF of G for functions from our input class. So the norm of f is smaller than 1, but information is 0. Okay? So we look at all functions giving us information 0, basically no information at all, and look at the worst function. And then we take the supremum of that. And what you then can easily, or what is not too hard to show, is that this, what we call here radius of information, is bounded from above and from below. From below by the 0 radius, and from above by twice the radius at 0. So we can as well study this radius at 0. And actually for the problems I'm considering here, we have even equality. This first line here is an equality in the cases I look at. That's why I will, on the following slides, only use the notation R and not R0, but we are always thinking about R0 here. So what is R0? Look at this line here. We have a linear information mapping of rank n, and we look at all elements, all functions f giving us 0. This is a subspace, right? This is an n codimensional subspace of f, and we look at the worst thing which can happen in the subspace intersected with the unit ball of f. And then we are already at this geometric setting, okay? We are looking for the radius of intersections of a unit ball of a normed space with n codimensional subspaces. I will come back to that. Okay, what Hinrichs really used was the minimal worst case error, which is not only the inf over phi, but the inf over phi and information nn, okay? So this is the inf over all information of our radius of information for this specific information, right? This is the minimal worst case error you can achieve. This gives you the complexity of the problem. Yeah?
Sorry, how it is related to Gelfand width?
This is basically, in the cases I consider, it's equal to Gelfand width. And if you, just a restriction here, if you allow arbitrary information, arbitrary linear information, right? So this inf over n is only about over the allowed information, okay? So if you allow what we call lambda all, the class of all linear informations, then this is within between the Gelfand width and twice the Gelfand width, okay? So for that you can really study the Gelfand width. This is a connection to approximation theory, but only if you take the infimum over all linear information. If you just take function values, this is different. Okay? Okay, let's get back to our problem here, or to our setting. We denote the optimal information you can use here by nn star. And the radius of the optimal information then is this worst case error. Of course, I'm ignoring that we have an inf here and not a mean, but this is not really essential. In our cases, it's really a minimum. Okay, and what do we want to study here? Okay, we have this optimal information, which is given by nn star. And now let's think about random information. Okay, so for some problems, it might not be realistic to really get the optimal information, either because you don't know what the optimal information is, or somebody gives you the information and it comes in rather randomly. What can you do then? Okay, so we think of L1 of f up to Ln of f as linear functionals, which are taken as IID independently distributed, identically distributed random variables. Okay. So this is now random information. And then, of course, you can go over to the probabilistic setting if you want. In the probabilistic setting, you would do the following. The worst case error somehow gives you a sup over all f with norm smaller than 1, right? This was our worst case error. If you now have random information, then you could put the expectation inside here, okay? So you take the expectation of f minus, or sf minus anf in G. Without this, this would be the worst case error. With the expectation here, you have a randomized error. This would be a Monte Carlo error, and usually, if you allow random algorithms, this gets smaller than the worst case error. But what we are interested now in is the expectation outside of the supremum here. Okay, so we look at random information, but then we want to have a deterministic algorithm using this random information. And of course, this thing here now is bigger than the inf over the sup, which is the optimal which comes from the optimal information nn star. Okay, so we are interested in an expectation of a supremum and want to compare this to the optimal information. Okay, here we have the radius of optimal information, which is the inf, and now we look at the expectation of the radii. Okay, so the general question is, how good is this random information compared to optimal information? Is it as good as optimal information? Is it a little bit worse? Or is it much worse? Okay, everything can happen, but for very interesting problems, you will see that often you have the same kind of error if you use random information or optimal information, and then you could say, okay, it's not so important to really find the optimal information. Random information does the trick. Okay, so this is a question. Let's look at an easy, basically toy example showing you what can happen and why random information could be as good or almost as good as as optimal information. And the problem is the following. We take Lipschitz functions, Lipschitz1 functions. Okay, this is our input space, and I already basically put the unit ball here, so this is already the set of all inputs we are using. And we want to do LP approximation for such univariate Lipschitz functions. Okay, and the information is now just function values. And then it's not too hard to show that for such Lipschitz functions, if you want to do LP approximation, P arbitrary between 1 and infinity, the best thing you can do is you take an equidistant grid at these points here. This is the optimal information. And the radius of optimal information, the minimal worst case error, is something between 1 divided by 2n for p equals infinity and 1 divided by 4n for p equals 1, and in between for p between 1. So it's always of the order 1 over n. Okay, this is easy. what we do now is we don't take the optimal information, we take n uniformly distributed points IID in the interval 0, 1, okay? And we compare that information with this here. And what you get then is, for p equals 1, actually you can prove a formula for the expectation of the radius of information, and it's n plus 3 divided by 2 times n plus 1 times n plus 2. So basically 1n cancels here, and you are back at information at radius of information 1 divided by 2n, a little bit larger for p equals 1, and see the optimal information, the optimal error was 1 divided by 2n. Basically it's the same what you get here. Okay, random information is as good as optimal information for p equals 1, L1 approximation. The same thing holds, but deteriorates a little bit if p goes to infinity. We always get the rate 1 divided by n, but the difference between the average radius and the optimal radius gets bigger and bigger as p goes to infinity. And for p equal to infinity, this gives you an additional log factor here. So now optimal information is 1 divided by 2n. Random information gives you log n divided by n. And this basically comes from because p equals infinity doesn't do any averaging anymore. You are looking for the biggest interval, for the biggest difference between two consecutive random points in the unit interval. And it's kind of well known that this gives you an additional logarithmic factor here. Okay? This is where this comes from, and you can go to higher dimensions, at least for this p equals infinity case, and to, in the one-dimensional case, to more general Sobolev spaces with this approach, and you get similar results. So here, for p less than infinity, random information as good as optimal information. For p equals infinity, you get a little loss, but it's not that important. Okay? So now let's come to our real problem. Our real problem is L2 approximation of functions from a Hilbert space, comparing random information and optimal information. Henrik already told you somehow what is the best information, and for our setting it doesn't change much just to look at sequence spaces. Actually it doesn't change anything. So we fix the singular values of these were the eigenvalues Henrik had of an embedding. These are sigma 1, sigma 2, and so on, ordered. And then we look at the following sequences in Rm, where m can be infinity or can also be finite. I'm mostly talking about the case m equals infinity. So you look at sequences x, which with this norm here. And this norm is, as you see, a Hilbert space norm, and it gives you, as a unit ball, something like this, an ellipsoid. Let's call that E sigma. This is the unit ball of this Hilbert space here. Okay? And the semi-axis are those singular values here. Okay, and we want to do L2 approximation. That means we measure the error in the usual L2 norm. Okay? This is a smaller ellipsoid than the canonical Euclidean ellipsoid, but in that norm we measure the error. Okay, so optimal information, as Henrik told us, is given by taking the corresponding eigenfunctions to the corresponding eigenvalues, the biggest ones, and in our case, since we have them ordered here, the optimal information is just the first n coordinates of x. Okay, this is optimal information, and the error you do is just the next singular number. Okay, the error, the nth minimal error is sigma n plus 1. So now the question becomes, random information, is it as good as this optimal information? Does it give something like sigma n plus 1 or not? Right? And what do we mean exactly by random information here? Okay, since we want to talk also about the case m equals infinity, we should take Gaussian information. Okay, so we take IID standard Gaussian random variables and we take as a linear functional this linear combination combining the coordinates with the Gaussian random variables. Okay, so if you are in a finite dimensional setting, if M is finite, then you can think equivalently of taking scalar products with Yj, where the y1 up to yn are uniformly distributed on the unit sphere. Okay, this gives you the same distribution as the Gaussian distribution for the radius of information. Right? Or you can do it in a geometric formulation for finite M. What was the expected radius of information? It was a radius of random sections, with n codimensional subspaces. So we take arbitrary n codimensional random linear subspaces, not arbitrary, random linear subspaces, according to the corresponding Haar measure on the Grassmannian manifold of those n codimensional subspaces of Rm. We intersect them with our unit ball here, so like this, and the question is, what is this radius here? What is the average radius you get here? Right? This is a nice geometric problem which you could formulate purely geometric, of course, and which was somehow also studied before. But I will come to that. So here I have a slide telling us that everything is okay for m equals infinity, but since I want to present the results, I'm going over that very quickly. Let's come to the results. What happens, and it was a little bit surprising at the beginning, is there is a huge difference between the cases that you have a flat ellipsoid, where the sigma k's go down fast, or you have a fat ellipsoid, where the sigma k don't go down too fast, and the breakpoint somehow is exactly L2. Okay? So if sigma is in L2 or not, this is what determines if you have random information is almost as good as optimal information, or if you have it is much worse, and in this case you really gain nothing by using random information about the initial error, let's say. So for sigma not in L2, you get that random information doesn't give you anything better than sigma 1, which is your biggest eigenvalue, the initial error. So you don't improve anything by using random information, even if you take many, many informations. But the positive side of it, maybe I should have written it differently. We should give the positive result first and the negative afterwards, but I mean...
Well, you are using the Polish notation.
I'm using the Polish notation. Yeah, okay. You improve things, right? Yeah, good. So let's improve things. If sigma is in L2, then the expected radius of random information tends to 0, and you already have on the boundary a fixed rate somehow. On the boundary between not in L2 and L2, you get already a fixed rate, 1 divided by square root of n, with which your error goes to 0. This looks like, this should be a capital O, I think. No? A small o? Okay, it's a small o. Okay, so good that I have my co-authors here who can correct me if I'm wrong. So you already get kind of the Monte Carlo rate for this random information. Okay, let's go a little bit more closer into the details, and let's look at some specific sequences. These are sequences going down polynomially, but maybe with an additional logarithmic term to see the real difference on the boundary. Okay, so if alpha is less than 1/2, the squares are not summable. If alpha is equal to 1/2 but beta is smaller than or equal to 1/2, the squares are not summable, we are not in L2, and we get this expectation here is equal to sigma 1. This is a bad case. Now things improve. if alpha is bigger than 1/2, we are in L2, and the random information, the expected value, gives you basically the same as optimal information. What happens at the boundary? So if alpha is equal to 1/2, okay, if we are not in L2, we are still in this case, but now we go into L2 with beta bigger than L2. Beta bigger means better, okay? The better is somehow hidden in the sigma n plus 1, right? The sigma somehow has the beta in it, but you lose something against the optimal information, and you lose again a logarithmic factor, okay? Square root of a logarithm here. So this is what happens for these specific sequences here, okay? So let me go into what was known earlier and why it didn't help us too much. As a geometric problem, this diameters or radii of sections of symmetric convex bodies were studied for quite some time in asymptotic geometric analysis. And the basic results about sections of symmetric convex bodies come from Giannopoulos and Millman from 1997 and 1998. I'm not going to present them here and go into details. There's subsequent work by Sascha Litvak, who is also here, and Nicole Tomczak-Jägermann from 2000, 2005, Giannopoulos, Millman, Zolomitis, and again Sascha and Pajor and Nicole Tomczak-Jägermann in 2006. There are more papers related to this, but especially this last paper was somehow one which we found first and used first, but unfortunately it didn't give the final sharp results. Okay, so these bounds are not only for ellipsoids, they are for arbitrary symmetric convex bodies, and as already Giannopoulos and Millman realized, they are not really optimal for all symmetric convex bodies, in particular not for ellipsoids with highly incomparable semi-axes. And this is basically the case we are also in. And the focus in those papers was on subspaces of, let's say, half dimension or half codimension or some proportional codimension. In our case, we have a very small codimension usually. So our m is much bigger than the n. N was the codimension, m the dimension. And the m basically shouldn't play a role in our results. So we look at spaces with very small codimension. But incidentally, one of our first approaches was based on entropy numbers, and the trick we took from the paper of Litvak, Pajor, and Tomczak-Jägermann. But this didn't, even specializing it to the case of ellipsoids, it didn't give the sharp results. I think we lost a rate 1/2 against the optimal rate, which is not good enough, as you see on the results. Okay. So what is involved in proving such bounds? Basically, we don't prove expectation bounds. We prove sharper exponential bounds for the radius of information, from which these easier to state average results follow. So let's look at the upper bound, which implies most of the results in our paper. If sigma is in L2, then we have the following. If we look at the L2 sum of the sigmas, but we start on a proportional level to n. So we start at n divided by 4. Then, of course, since we have a sum here, we lose something against the sigma n, which could be comparable to sigma n divided by 4. But we gain something by the square root of n. So this is a large deviation result here. The radius is bigger than this. The probability of that to happen is very small. So usually the radius is smaller than this, and this gives you, in particular, the upper bounds for the expectation I stated earlier. Yes. So what tools do we need? What we need are, okay, what do we have? We have independent standard Gaussian entries in a matrix, which gives us the information map. Okay. So what we want to study are those sections here. We study the sections of the ellipsoid E sigma, which I have drawn here, with the null space of the information, right? This is the geometric formulation of the problem. What we really need to look at are submatrices of the whole matrix. So we look at submatrices indexed by I and j. I and j are subsets of the integers. And we also look at structures Gaussian matrices. So here all the entries are identically distributed. Here we have this factor sigma j coming from our ellipsoid. So we also look at those structured Gaussian matrices here. And then we prove a bound, fixing the matrix. We prove a bound on the radius, looking like this. For each k smaller than n, you have sigma k plus 1 as one term, fine. And you have a quotient of two singular numbers. These are singular numbers of the corresponding matrices. What you have here is basically the norm, the first singular number of such a structured Gaussian matrix. We just kill the first k columns of that matrix and keep the rest. And here we keep the first columns but take the smallest singular value of that submatrix. Okay? So this bound of the radius in terms of singular values is nice because in the last 10-15 years lots of research was done on singular values of random matrices, and what we can use then are lower bounds for the smallest singular value of such Gaussian matrices. Actually what we use is from a paper of Bandera and Van Handel from 2016. And about the largest singular value, the norm of such a structured Gaussian matrix, and there it is enough to take a result of Davidson and Sharek from 2001. I think there are better results proved later on, but for our purposes this is exactly what we need. Okay, so if we have a bound from below for this thing and a bound from above for this thing, a bound from below for this thing, then we can bound this further from above. And of course these are probability bounds here, and all together you get this bound if you put that together. Okay, for the lower bound you can do something similar. This is the basic pointwise, let's say pointwise estimate. If sigma j, if the sum of the sigma j squares has some size, written down here, then the probability that r is very small compared to sigma k is very small. This gives you the bound in the other direction. Okay, and what you then can use there is again a bound involving singular values and bounds for the singular values coming from Gordon's mean-max theorem from 1988. You need concentration of chi-square random variables because you have squares of Gaussians involved there. We use in the paper a result of Laurent and Massard. Or you can also use concentration of Gaussian random vectors in Banach spaces. Both give the same results. Okay, these are the tools for the lower bounds. And this is basically what I wanted to say about the problem. Average information versus optimal information, random information versus optimal information. You have seen sometimes it's bad, sometimes it's good, and I think it's a problem which is worth to be studied in more generality and other contexts and so on. I want to finish with a nice analogy. We have some kind of a similar discrepancy, kind of a similar dichotomy. If you look instead of the difference between random info and optimal info for the difference between general linear info and function values. There also somehow the case sigma in L2 is kind of a breakpoint. Not everything is as clean as we have it in the random setting here in this setting. There are still important open questions for this thing here. Right now it is somehow only kind of an analogy, but maybe there's something hidden behind connecting the random setting I told you about in this talk with this lambda all, lambda standard problem here. That would be really nice to have some connection, because then it would be, I think it would be reasonable to expect that we here basically have the same kind of results. If you are in lambda 2, then lambda all and lambda standard are pretty much of the same power, which would be nice to have, and we don't have that now. My time is over. Thank you very much for your attention.
Thank you very much, Aicke. Are there any questions, comments?
Oh, yeah, if nobody wants to ask a question, can I see slide number 16, please?
Did I have so many slides?
Well, you have 24.
Oh, really?
Oh. Okay, so I want to ask you about because you have an equivalence. Let's assume that always alpha is greater than 1/2.
So this case here.
Yeah, the last one, the positive case. Do we control the constant? No, I'm thinking about tractability. Because I think for your proof, it looked like the constants are absolute.
Yeah, that are absolute constants. So you can use them also for tractability results, right? I mean, you have to control the sigmas, so you have the same problem for tensor product problems as you presented here, but then you can say, okay, random information is as powerful as optimal information. Constants don't. If you look at it from the point of view of tractability, it's even stronger than it looks, right?
Other questions?
This is nothing to do with information, but in some material science applications, there are one takes sections of three-dimensional ellipsoids, but not with planes through the origin like you've done, and you want to know about some statistics of the ellipses that you get. Do you know any papers on this in this area?
For the three-dimensional problem specifically, no, I don't think we looked at, because for us, of course, higher dimensional problems are is the key thing, because we want to let go the number of informations to infinity. So I don't know about any fine statistics for those things, but I'm pretty sure that you can compute at least the expectation of the radius here for these specific cases, because you just have, I mean, planes. You want planes actually, right? So one codimensional spaces. This should be possible even for planes not going through, but maybe you know more about that. Would be so I don't know.
Other questions? I have a little short comment, just to make a connection, because this approach is choosing the random subspace. It used to be, like if you look at the breakthrough result of Cauchy from 1977, when he found the bound, the optimal bound for the Kolmogorov width, so the Euclidean ball in L infinity, then the proof was exactly like this. I think it's looking at random subspaces, and he proved that. But in that case, we still don't have a constructive proof. But anyway, so this method is really good, and this is one more example. I mean, it works very
Yes.
well.
This is a very good example for making the point, because there you also don't, I mean, okay, I don't want to, but this is an example we also looked at. It's recovery of L2, recovery of L1 vectors in L2, if you want, all right? So the problem is recovery of vectors, and the basic work from the Russian school is of course well known also in compressed sensing and so on. This is what can also fits very well in this general framework. But here we actually know the optimal algorithm. This is a difference to this case, right?
Okay, in order to keep by schedule, let's thank the speaker again.